Let's go over an acid and base past paper question. It does involve a titration as well as calculating pH. Let's do it. So first question says a standard solution. Remember, a standard solution is a solution that I know the concentration of, a solution of known concentration. We prepare this by dissolving 10 grams of sodium carbonate. They give you the formula in 0.7 cubic decimeters of water. My first question is to calculate the concentration. So this is the formula sheet as given in your final exam paper as well as your exam guidelines. Concentration, it's either going to be this formula or this formula because they give you the mass in grams. I think it's easier to use this formula. This formula, essentially the one that I'm showing you now, is a combination of these two. So I'm going to use this formula. We then substitute, so blank formula first, then 10 grams. My molar mass, remember it's Na2CO3, so it's 23 times 2, that's the sodium, plus 12 for the carbon, plus 16 times 3 for the oxygen. I get 106 is my molar mass, and my volume must be in cubic decimeters, and it is, so 0.7. And I get an answer of 0.13, rounded off to 2 decimal places, mole per cubic decimeter. Please take note how my unit is dm to the -3. That's your unit for concentration. Now the next question says, will the pH of the solution, so what solution are they talking about? Remember, they're adding this sodium carbonate to water. Will that pH of that solution be greater than or less than 7? Okay, now what they don't say in so many words in this question is that when we take Na2CO3 and we dissolve it in water, a process called hydrolysis happens. So hydrolysis is the reaction of a salt. So in this case, sodium carbonate is my salt. It's a reaction of that salt with water. And when we test the pH of that final solution, it'll either be greater than 7 or less than 7. And there is a way to determine this. You need to focus on working out the hydrolysis. How does this work? So you look at the salt, Na2CO3. This is how I teach it at least. You need to know that this salt, Na2CO3, is made up of the following ions. So we've got the sodium ion, Na+. I know there's a 2 over there. It's because there's 2 sodium ions. And then the carbonate ion, CO3, 2-. The sodium ion and the carbonate ion. Those two things come together to give me sodium carbonate. Then something else that you need to know is that the Na+ ion, the sodium ion, comes from NaOH, sodium hydroxide, which is a strong base. Okay, so the base is strong. The CO3 2-, this carbonate ion, what that comes from is a weak acid, okay, called carbonic acid. So it comes from H2CO3, which is a weak acid. Now, how do I know that it comes from an acid and a base? All salts, so this is a salt, come from a reaction between an acid and a base. Remember, as I taught you in my lessons, an acid plus a base gives me a salt plus water. It can give me other products as well, depending on what the base is, but generally speaking, acid plus base gives me a salt and water. So if I have a salt, like I do in this case, Na2CO3, I can work backwards to figure out which base and which acid produced that salt. So in this case, Na2CO3 is produced from or came from a reaction between NaOH and H2CO3. Now, NaOH is a strong base. H2CO3 is a weak acid. If strong has to fight with weak, if I have to put them in a match together, who's going to win, the strong or the weak? I hope you say the strong wins. And because the base is strong, what that means is that the overall solution will be basic or alkaline. And that means that the pH of the solution will be greater than 7. So your answer is greater than. So generally speaking, the salt comes from a reaction between an acid and a base. In this case, the acid that produced this salt is carbonic acid, is a weak acid, and the base that produced the salt is the NaOH, which is a strong base. The acid is weak, the base is strong. The strong one will be the winner, and because the base is the winner, the base is strong, that means that the pH will be greater than 7. Now they say, write an equation that explains the answer to 7.1.2. So this is basically writing our hydrolysis equation, and like I taught you, when you do a hydrolysis equation, you have your pick. One of these is going to react with water, either Na+ or CO3 2 minus. One of those two ions is going to react with water. When you have hydrolysis, the weaker ion reacts with water. So again, if we have Na2CO3, we said that this can be broken down into Na plus and CO3 2 minus. These are the two ions that make up sodium carbonate, Na plus and CO3 2 minus. We have to pick one of these is going to react with water. It's always the weaker ion. So we said Na plus comes from a strong base. So that's not the weaker one. Na plus is the stronger one. CO3 2 minus comes from the weak acid. So in our case, it's this weak ion, CO3 2 minus, that will react with water. We expect for the final solution to be basic solution with a pH greater than 7. And you should know that a basic solution would have OH minus hydroxide ions floating around in it. This is what we expect to see if it's basic, the presence of hydroxide ions. If it's acidic, then we expect to see the presence of hydronium ions, but it's not acidic. We said the strong person wins, the base is strong, so therefore we expect to see hydroxide ions. What this means is that in this reaction, the water must have given away an H plus ion, a hydrogen ion. Think about it. If H2O gives away an H plus, that's why the H2O becomes OH minus, and this H plus is going to join up with CO3 2 minus to form HCO3. It's no longer going to be 2 minus because it's gaining a proton. It's just going to be 1 minus. So this over here that I just wrote out, this reaction over here, is my answer to 7.1.3. You would write down that reaction. You don't have to draw in this arrow over here or anything like that. Just this reaction is perfect. What we can also do is we can balance this reaction. So what we could do is give one of the following as our answer. So my answer was this first one over here, which is how I teach hydrolysis. This is the first option on the memo. Or you can do the balanced reaction. So in other words, we've got the carbonate ion reacting with 2 water molecules to form 2 hydroxide ions, and then this would then form H2CO3. This would just be balanced essentially. There's another way that we can represent this. We can practically take the whole salt. So this is taking the weaker ion, which is the typical way that we explain hydrolysis. The weaker ion reacts with the water in hydrolysis, and it forms the OH minus ions, the hydroxide ions, which indicates that the pH of the solution is going to be greater than 7. It's going to be a basic solution because remember the base was strong in this reaction. Or what you can do is you can take the whole salt and react it with water, and your products would then be my acid, my carbonic acid, which we said was weak, and then my base, which we said was strong. Just be careful and balance depending on which option you do. Like I said, I teach the previous option that I just showed you. So I do the first option on the memo. If you want to see more videos on that, just please go check that out. But 7.1.4 says which one of the indicators, P, Q, or R, is most suitable for this titration. Okay, now let's just read carefully. It says the sodium carbonate solution. So Na2CO3 is titrated with dilute hydrochloric acid. These two are titrated against one another, and we have the indicators that are available. So as you should remember when we talked about titrations, is that, for example, we have the acid solution that we put in this Erlenmeyer or conical flask. We use a pipette and we measure an exact volume, for example. Then we add what we call the indicator into the solution. We then, step by step, drop by drop, add the base into the acid until neutralization takes place and until the indicator has changed color. And as I told you, we pick our indicators depending on the type of acid and the type of base that reacts. So in this case, we've got HCl, which you should know is a strong acid. And we've got Na2CO3, which is a weak base. Remember, this is a new situation now. We're adding HCl to Na2CO3, HCl strong acid, Na2CO3 weak base. So who is going to win? Strong will win over weak. So the acid is strong, which means that the equivalence point of the titration should be less than 7. Remember, if we take a look at the pH scale, we've got 0, 7, which is neutral, 14. If you are above 7, below 14, then that's basic or alkaline. If you are between 0 and 7, so less than 7, that is acidic. So, because I have a strong acid and a weak base, the acid will win, the acid is stronger, so therefore my pH will be somewhere in this range over here, less than 7. So that means that we will go for indicator P because the pH range will be less than 7. So I'm saying P, the titration of a weak base and a strong acid, therefore the equivalence point is lower than pH 7. Okay, 7.2. When 0.01 moles of dilute sulfuric acid is mixed with 0.024 moles of potassium hydroxide, the total volume of the solution is 0.2 cubic decimeters. So once they add the acid and the base together, the total volume is that. First of all, they say what is meant by a dilute acid. So this is essentially sort of like a definition. We've spoken about dilute versus concentrated. So remember, a substance can either be dilute or concentrated. That is very different to strong versus weak. So you can, for example, be dilute and strong. So sulfuric acid, H2SO4 in this case, is strong. It's a strong acid, but it's dilute in this case. So dilute just means it contains a small number of moles or amount of moles of acid in proportion to the volume of water. If you think about how you work out concentration, dilute has to do with concentration. It means that your volume of your water is very big, so your V is very big, and your N is very small. That's essentially what it means. Then 7.2.2, calculate the pH of the final solution and take note how it is 8 marks. So we know we're going to have to be doing quite a lot of working out. As you should know, to calculate pH, we eventually want to make use of this formula. However, we first need to take note or look at the question very carefully to see if when these two things mix together, because what we're doing is we're adding sulfuric acid, so let's call this H2SO4, we're adding that to potassium hydroxide, KOH. And what's important to note is they don't say that these solutions completely neutralized each other. We don't know if the H2SO4 and the KOH fully reacted with one another. What could have happened is that there could be some leftover H2SO4 or some leftover potassium hydroxide, and that will therefore affect the pH of the final solution. So if we have some acid left over, then we know acid, that is connected to the amount of hydronium ions, and then we can jump in and use our pH formula. But if we have some bases left over, then we know we're going to have some OH minuses left over. We are then going to have to potentially use this formula over here with the OH minus to calculate the H3O plus and then make use of this formula. So try and stay with me as we speak about this, but just know that we're adding an acid and a base together. And we know that they react in a 2:1 ratio. So what we know at the moment is we know the moles of H2SO4 that are added is 0.01 moles. Now remember, we don't know if all of this is going to get used up. We know the moles of potassium hydroxide that is added is going to be 0.024 moles. Now again, we don't know if all of that 0.024 is going to get used up. So what's the easiest way to figure out how much is actually going to get reacted? You need to use your mole ratios. So as I mentioned earlier, the base and the acid react in a 2:1 ratio. Remember, it's the big numbers in front of them. So we go like this. KOH reacts with H2SO4 in a 2:1 ratio. Now, let's say I want to use up all of the acid. If I want to use up all of the acid, I can work out how much of the base would react with the acid. So what I'm doing is I'm taking the mole ratio and I'm saying, if I want to use up all of the acid, so 0.01 moles, if I want to react all of this, how much base would I react? To figure out how much of the other one would react, I put it in a mole ratio. Now, how I do mole ratios, I think this is a very simple ratio. How do you get from 1 to 2? You multiply by 2, so then you would multiply this by 2. So what this is telling me, I hope everybody understands this, is that I would, if I react 0.01 moles of the acid, I would react 0.02 moles of the base. KOH would react. Okay? So what I'm saying now is if I react all of this acid, then I would use up 0.02 moles of the base. But how much base did I tell you we had at the beginning of the reaction? This is how much we have at the beginning. So if you need to make notes, this 0.024 is the amount, the moles of KOH base that I have at the start. Then I use the mole ratio, and the mole ratio tells me the moles of KOH that will actually be used up or that will actually react. Now, can you see that I'm not reacting everything? I have some left over. I'm reacting 0.02, but I have 0.024 at the start. So what we do is we take what we started with, 0.024, minus what we use up, 0.02, and the difference, 0.004 moles. The difference, that's the moles of KOH that is in excess. We call it excess, or we can also say that is left over. So just to break it down, we had 0.01 moles of the acid at the start. All of this reacted. And we used the mole ratio to figure out how much base would react. We said 0.02 of the base reacted. But we had 0.024 of the base at the beginning. So therefore, what's left over in the container is 0.004 moles of KOH. So if you think about it, all the acid is gone. 0.02 moles of the base, gone. It's reacted. All that's left over in my little container, so in this volume over here, remember the volume once we combined the substances was 0.2 cubic decimeters. In this 0.2 cubic decimeters, the only stuff that I have left, besides the products and stuff, the only leftover stuff that I started with, from what I started with, is a 0.004 moles of base that is left over. What I now know is that I know the moles of the base, as I said, is 0.004 moles of base is left over. I also know that this base, how it breaks up in the water is as follows. It forms K plus and OH minus. Do you see that this dissolves or dissociates in water in a 1-to-1 ratio? What that means is that if I know the concentration of the base, then the concentration of the hydroxide ions would be exactly the same because it's a 1-to-1 ratio. Potassium hydroxide is also a strong base, which means it dissociates completely in water to form a high concentration of hydroxide ions. So again, it means that if I know the concentration of the base, I know the concentration of the hydronium ions. So how do we work out concentration? C is equal to N over V. We know the concentration is 0.004, and as mentioned, the volume here is 0.2. They tell me that, 0.2. That means that the concentration is 0.02 moles per cubic decimeter. And again, the concentration of that base is the same as the concentration of the OH minus ions, which is 0.02 moles per cubic decimeter. Reason why they're the same, 1-to-1 ratio, and KOH is a strong base. Now, why do I care about the concentration of these ions? Remember, I said that I'm trying to look for pH. To work out pH, I need H3O plus, but first, what I have at the moment is OH minus. So what we're going to do is we're going to make use of the KW formula first. So we're going to say, okay, we know that KW is equal to the concentration of the hydronium ions multiplied by the concentration of the hydroxide ions. And we know that KW, look at it, it's a constant, is 1 times 10 to the negative 14. So that's 1 times 10 to the negative 14. I don't know at this stage the concentration of my hydronium ions, but I do know my hydroxide ions is 0.02. Okay? To get the concentration of my hydronium ions alone, I divide both sides of the equation by 0.02. So I say 1 times 10 to the power of negative 14 divided by 0.02, and I get 5 times 10 to the negative 13. That is the concentration of my hydronium ions. And now that I have that, take a look. I have this. Yay. I can now work out pH. So you write your pH formula. Remember, I have to tell my learners this all the time. It's a baby P and a big H. Please write it nice and neat to get your formula mark. Your H3O plus has to be in square brackets. Don't make the marker guess if you're writing square brackets or round brackets. And then substitute in. When you sub in, you can use round brackets. 5 times 10 to the negative 13. Don't forget your minus in the formula. And I get a pH of 12,30. No units, round off to 2 decimal places. That's my final answer. Sure, what a tricky one. I really hope that was okay and that you understood that. Please give this video a thumbs up if I helped you today. Comment down below what you want to see next. And please, if you're not subscribed yet, please subscribe. And I can't wait to see you in another video very soon. Bye, everybody.